Okay, hello, welcome to the second part of today's summer course. So I am going after Renzo, therefore I try to keep this section much lighter on top of all these artifacts and how to change them and all the parameters from the scanner side. I will talk about the part once you get the data. So you went to your MRI physicist, he or she did lots of smart tricks to get the best data available, and you have the data, and now you have a task to do, which is to analyze it. And usually, because we are doing layer fMRI in this course, we are interested in the gray matter, so we need to do segmentation. So I will talk about it first. But even before that, I would like to justify why am I talking, because instead of just like pushing some ideas on you, like I would like to justify that why I might have a unique perspective on the issue of segmentation, and especially like challenging segmentations. So easy, I wrote a paper on cortical segmentation using 7T data, like including both MP range, like T1 weighted traditional, and MP2 range, like standard data, and how to really tweak it and optimize it for the precise and accurate gray matter segmentations. It's available in this reference. Also, we developed a toolbox for it, a software package. Then I have segmented quite a lot of non-human primate brains. These are ex vivo brain images acquired in MRI. But of course, like they come with lots of other problems. They are just like brains in jars, so to say. But not so to say, they are, and they are scanned. And we had to analyze the shape of them together with my friends from Paris, Katya and Roberto. And I selected like the hardest images in these and segmented them to contribute to this project. You can read the project further in Career et al. 2019. I have also segmented lots of brain stems because part of my PhD project was about the human brain stem. In vivo and ex vivo images, histology images, I looked at the literature, tried to understand how people were talking about segmentations before and translate them in 3D, which is not an easy task to do. You can read it in this reference. I have segmented vasculature images from images acquired at 9.4 Tesla MR in Maastricht, which were very exciting in 2 years ago at 2.25 millimeter isotropic resolution in vivo. And we could see like arteries and veins differently, and I could segment them and do some analysis on them. So this is a work in progress, but you can check the poster if you are interested. And also I do segmentations for fun. For instance, here you can see that I segmented the dolphin brain from the brain catalog project, again in collaboration with Katya Hoyer and Roberto Toro from Paris. I segmented one hemisphere of this dolphin brain, which is huge and very complicated and very challenging, and then constructed some surface meshes and inflate them and play around with them. So I do segmentations all the time, not all the time, but most of the time, and I do it even for fun. So first, I would like to talk about the reason why we need to segment. Probably this is very people kind of know this implicitly, probably, but I just want to make it explicit here. Well, we want to understand what the neurons are doing because we want to understand how the brain works. And in this current age, people think that how brain works relates mostly to neurons. By the way, which wasn't the case. For instance, in the 1800s, people thought that the psychology of the human was related to the ventricles, right? So now we think they are about the neurons, and probably we are more correct. But like we try to do all these things because of some like very deep assumptions. Well, therefore, we need to know which voxels contain our neurons. Voxels are our sampling elements in MRI data. And cortical gray matter, we know that it contains neurons mostly, and the layers that we are interested in this layer fMRI analysis and acquisition course. Therefore, we need to know which voxels contain gray matter tissue. How do we segment, and what is the best tool? So I can already anticipate that some of you are looking for maybe a course like showing you how to use some of these tools or what are the best solutions, like SPM, FSL. I'm sure that many of you use at least a few of these, FreeSurfer, CBS tools, and with this new name, NIRES in Python, Rainbow ITK, Snap Slicer, and many others. Everyone has a favorite way of segmenting brain images and different data modalities. However, this course is not about what is the best tool and how do we segment, at least not right now, maybe in the next lecture. So I really believe in this motto, which is like give a person a fish and you feed them for a day, and teach a person to fish and you feed them for a lifetime. So I'm gonna not teach you how to use certain tools and what are the best solutions under certain stress, but I want to really show you how I think about it, like the general issue of segmentation, and how I go about trying to select my tools to address certain issues in it, without telling you which tool I really use, at least for now. Of course, like the answer to this, what is the best tool in which situation, can be entertained later. Okay, so to me, there are three approaches. One, manual, and you just trust experts. There is an expert, for instance, one of the participants, Minwei Zhan, I know, is a very good expert on how to segment brain images manually. And then there are lots of people who like to use automatic approaches and put their trust in machines and think that machines are just better overall because they are not humans. However, let me remind you that all these machines are built by experts. So they kind of inherit certain thoughts and assumptions of these experts, any like pipeline, any algorithm, any machine that you use to automate. And the third approach, which is the one I like the most, and I think this is the right one for the ultra high field data and for layer MRI related studies, which is something in between. So as you can see here, the user is loading the logs into the machine. Machine is very mobile. It's not like a huge vehicle that you need to drive on top of the mountain, which you cannot do anyway, but this person can just go at the top of the mountain with a small and mobile machine, and mixing a bit of manual labor with some automatized pipeline, he can do his job. And of course, we need to remember that whatever method we use, whether it's a big machine, a big pipeline, or manual segmentations all the way, or something in between, we want the results. As long as we get our logs chopped and fireplace ready to make us warm in the night, we should be fine. So I would like to remind all of you that whatever tool method you use, if the results are good enough for you, of course, that's another question, how to test they are good enough. It should be fine. And let me remind you another thing. Expertise is choosing the right tools for the right situations. This is really what I believe in, and I will really try to convey how I think about segmentation. So use the tools at the right time, use the tools in the right way, and use them on the right problem. And this expertise develops over time, of course, as you use different tools, experience different situations, and know what to use when and in which way. So how to build expertise? Of course, like one way to build expertise would be to just exactly you going through like all these challenging data sets and segmentations that I went through and build what I know until today, and maybe then do some other things and build further. But I think to convey some expertise very quickly, we can really make use of the toy models. This is what I personally really strongly believe in, which might not be agreed upon. But since I am talking right now, I will just show you some of my toy models. So here, I'm going faster than I expected actually. So here I am starting from a very, very simple toy model that I call the simple head. You can see there is the skull, eyes, nose, very simple brain with one ventricle in it, lots of white matter, and around the edges, gray matter. And here we are looking at a picture, a measurement of this image in such a way that we have infinite resolution, which we of course never have. And the tissue boundaries are infinitely sharp. If you look at the histogram of such an image, then you will see only three peaks, which is one for the white tissues, eyeballs, the skull, and white matter, around 240. And no variation, right? One for the gray matter, which is around 130, and 1 for the CSF, and of course for the air, which is 0, but you can actually see it here. So okay, we have 3 different signals from various tissues, but they give the same signal in this contrast. However, of course, we cannot measure things with infinite precision and infinite accuracy. If we could, it would be nice, or maybe not, but we cannot do it. Therefore, there's no point discussing about it. Our images usually look something like this, more pixelated or voxelated, right? And we have to just use these images and get something out of it with regards to gray matter segmentation. So here, I have just, as you can see, like down sampled like the image a little bit, so you can see the difference. And now, at each voxel, which I here use a notation for some of you who might be liking the notations more, just a signal for S and voxel N, which means that one of these voxels, like voxel 1, 2, 3, and it goes up until N. For a given voxel, what we measure is some multiplier, and I will explain this, with the tissue that is in it, plus another multiplier with the signal from another tissue. And you can think of it like, for instance, in this voxel here, between white matter and gray matter, the weight 1 can be 0.5, like half of the voxel is real white matter, true white matter. So signal from the white matter tissue plus other weight 0.5 from the gray matter. The half of the voxel is occupied with the pure or true gray matter tissue. So signal from the gray matter. So what you would measure at the end would be the signal that is in combination with the white matter and gray matter. And this effect is called partial voluming in MRI. I mean, a simple way you can think of it. Like, of course, there can be more tissues, like maybe there are interfaces where 3 tissues meet. And the signal that you will measure will be a combination of, or a composition of 3 different tissues. And now let's have a look at the right-hand side, the image histogram. So all the intensities, and the range is unsigned integer 8, which is 0 to 255. And here I put the counts, so how many voxels are at that intensity. And you can see that from the ideal object case, which we have only 3 sticks that goes up until infinity counts-wise. In this sampled image, discrete image, we still have lots of strong peaks and lots of voxels that are within these peaks, but we have something in between to see this area. And all these intensities are generated due to the partial voluming, which we always have in MRI data. Okay, so this is one of the variations in our signal. And we are now set to understand the parts of our signal, right? So to understand the parts of our signal and then to understand how we deal with certain variations in our images to do the good segmentation, the useful segmentation. Okay, next, the bias field, or also called inhomogeneity field, intensity, non-uniformities, and so forth. There are lots of names for it, but here I choose to call it bias field. Do you see the difference? This part is brighter than that part of the image. If you contrast it with the sampled image that we saw a step before, and now look at the same image with the bias field, you can also see the change in the histograms. So now all the counts are went down, yet we still have 3 peaks for 3 different signal categories. However, in between, we have even more voxels that fills the gaps. So our image is becoming more and more troublesome in terms of like easily segmenting or determining which voxel belongs to which tissue. Because like here in this sampled image, you can see that around the peaks, or maybe if you put like a boundary in the middle between 50 and 130, whatever falls on the left-hand side is the CSF, let's say, the ventricle tissue or material, and whatever falls on the right up until some other boundary is the gray matter and so forth. However, Now, in between parts are getting more messy, so we might see voxels that are mislabeled as gray matter or white matter, whereas they should be the other way around and so forth. And here, this effect can be thought of as a multiplication of your signal that comes from a mixture of tissues. And if you are lucky, just a pure white matter or pure gray matter, multiplied with some bias field. And these can be there for lots of different reasons. And your MRI physicist will try to reduce most of these, but you will still end up having some in the data. And now you need to correct that to have the description of your voxels appear more straightforward in the histogram, so that you can exploit some properties in the histogram to categorize these tissues. So now I would like to show another effect. Now we went back to the sampled object. There's no bias field anymore. But now we added some noise. And this is what I call just a thermal noise, or here Gaussian noise. Specifically, I very straightforwardly just generated some noise field and then added to the sampled image. You can see that this is an additive effect. So it is the signal of the tissue mixture that we measure plus just some measurement noise, thermal noise. This will be always there too. You cannot really get rid of it. You can try to reduce it in the acquisition part, but whatever you do, there will be thermal noise in your images. And look what happens to the histogram. 3 different peaks and one hidden one at 0, because we have all the air voxels with 0. And now adding thermal noise, all these sharp peaks are gone. But we still have something here, another there. But the peak around the so-called CSF tissue, ventricle tissue, is almost gone. And everything 0 kind of started to fill in a bit more higher values. So I'm now simplifying lots of things, but hopefully in the next lecture I will go much more in depth and also give you some empirical examples, not only toy examples, but I'm now trying to build the foundation for it. Okay, and now I will put 2 of these effects in it, the bias field and the thermal noise together. So you can see that this part is kind of brighter than that part, and also lots of noisy pixels or voxels are in it. And have a look at here. Now we have a histogram with basically no straightforwardly visible peak in it, just here, but that's for the air tissues, and because there are a lot of pixels that are 0. And usually this is the place where we start from in our segmentation journey for MRI images. Of course, it's maybe a bit more noisy one. I just exaggerated a few things in it. But this is really the idea. We start from here, and we try to go back to the ideal case, then try to determine which voxel is which tissue, gray matter, white matter, CSF, or something else. Okay, now our signal consists of the mixture of the tissue signal multiplied by the bias field plus the thermal noise term at the end. So one multiplicative term and one additive term added to our signal, and it became our measurement, where we start from. Well, you might know that very first step of doing brain segmentation is to do brain extraction. And there's a reason for it, of course, a very good reason. And here I'm just doing a brain extraction, this red mask I use to mask out everything outside of the brain, which is a very simple brain here, of course. And I just left a little gap to kind of simulate the realistic scenario a bit better, so that it's not perfectly tight around the gray matter, but it's a little bit larger. So, okay, now let's see what happens to our image and our histogram once we mask out. And see, we get rid of all the useless voxels outside. So this peak here is completely gone. All the eyes, the tissue, and you can see that some voxels are gone from here too, which is good because the skull and the eyes and the noise were mixing with our white matter, which we do not want. We only want white matter, gray matter, CSF, possibly. before we start like more further segmentation. And you can see that in the histogram we are cleaning it up. So this might be very straightforward, but the point here is that if you are interested in a very specific region of interest, and if you know where it is, and maybe if some default like segmentation pipelines are failing already, you can try to really tighten your region of interest first, so that the image descriptives, such as the histogram, looks much cleaner. And maybe you know what to do better. Of course, we still do not see much peaks in it, maybe 1 year, 2 years, maybe. And now, this step is not, I think, commonly used at the beginning, but in the next lecture, I will show a few ways of doing it, and also like one that I implemented, so I know a bit more in detail how to do it. But I think it would benefit us if we have a very noisy image, we start trying to remove the thermal noise first. I mean, of course, this is a very hard thing to do. You cannot just estimate and remove the thermal noise like that. But here, just for the argument's sake, because I added the thermal noise, I just subtracted, and thinking that I can do like a perfect thermal noise estimation from my data, and subtract it and see how the histogram changes. You see that almost there is nothing usable to something usable, some peaks. But still we have other stuff. So this might be like a first step of removing the noise, one of the noise terms from your data, if you have very noisy data to start with, to try addressing the thermal noise issue, all these like voxel-wise noise. And then, of course, we try to remove the bias field. And this is implemented by default in lots of segmentation pipelines. Like there are many algorithms to estimate the bias field and try to remove it by dividing it and so forth. And here you can see that I divide with the estimated bias field, which I can do here perfectly because I created the bias field, but you will get some estimation of the bias field, which will be, of course, not completely perfect, but it will be close, so that you will see in the histogram the peaks getting larger and larger. So the point here is that in your measured image, you will start from here, and every step that you do in the segmentation pipeline should improve the image descriptives in terms of giving you sharper and sharper peaks, more tighter regions of interest, and addressing large and small scale noise sources, which we saw two of them here as the thermal noise and the bias field. So bias field is the large scale noise, and the thermal noise is the very small scale, voxel-wise scale noise. And of course, this is much easier to segment, to know which tissue, which voxel belongs to which tissue, white matter, gray matter, or CSF. It's okay. 23 minutes in. So there are three major sources of signal variation to remember, and these are really the major sources. Like anything that you can do to address these will significantly improve your data quality. There are lots of other terms too and lots of other artifacts too, but I hope to show it in the next section. This is just like a simple introduction. One is the partial voluming. Unfortunately, you cannot really remove partial voluming before making strong assumptions of what's underneath. You can remove it by acquiring high resolution data, so it's not really a solution if you cannot acquire new data. Two, thermal noise. This can be addressed with a few algorithms that would improve your image statistics. Of course, like all with some assumptions, so therefore they will perturb certain aspects of your image, maybe in undesired directions, but we are always trying to win more than losing. So as long as you win more with any filtering method, you are on the right track. And third, the bias field. There are also, again, lots of algorithms to estimate it and remove it. And if you overdo it, you might introduce even more inhomogeneity to the image sometimes. But remember that whatever you do, you look at the histograms and see the desired changes that I showed you right now. So the peaks are getting peakier and tighter and so forth. So now next up, I would like to switch from this toy model, simple head, to a more realistic model, which I used a lot and learned a lot from. This is not 7T stuff, like this is 3T data, like 3T based simulation. It's called BrainWeb. So you can go to this website, you can select the normal brain data space. If you are interested in like lesions, there's another multiple sclerosis lesion brain database too. And then you can select your modality T1, T2, PD, then select your noise level, for instance, 0%, like a perfect measurement almost just with partial volume and higher levels of noise. And this is the like thermal noise that I mentioned, is the same thing. And then the intensity non-uniformity noise, which is the bias field that I have mentioned. So you can download a few of these, have a look around, maybe pass them through your favorite segmentation algorithm to see how it behaves. For instance, what I like to do is to just start from 0% noise and 0% intensity non-uniformity. So it's like a very good sampled image just with partial voluming. I have that, pass it through some algorithm, and then I have the most noisiest one, or you can generate your own noise and add to it, and pass it through your favorite segmentation algorithm again and see what's different. And this would give you lots of insights of maybe which parts the pipeline is failing, or which parts it's really doing a good job, and so forth. So this is really for validation. In the next session, I will start from this a bit more realistic model, together with showing you more examples from 7T and maybe 9.4T data, like extremely challenging cases. And for now, thank you, and to be continued.